Hello, everyone. We'll get started in just a moment. Hello, this is Leah Freeberg from Fluke Reliability, and thanks for joining us today for this Best Practices webinar. You probably know Fluke is a test tools provider, and you may also know that we produce some of the industry's favorite reliability tools, from infrared cameras to vibration meters. But you may not know that many of the measurements that our tools collect now flow automatically into EAM systems of record. It happens via a framework that we call Fluke Accelix. Our goal at Fluke Reliability is to better connect asset management data and teams with asset management systems to drive connected knowledge. And of course, that knowledge depends greatly on best practices in condition-based maintenance. So that's why this series of webinars explores reliability maintenance strategies. That's why we feature speakers from a variety of expert backgrounds. Before the presentation, we have a few housekeeping items to go over. Today's session is being recorded, so your phone lines will be muted to minimize background noise. We will be answering questions after the presentation during Q&A. But take a minute now to find the questions tool in the GoToWebinar dashboard, and please feel welcome to submit questions as we go. I will share as many of your questions as time allows for our presenter to answer. If we have unanswered questions at the end, we'll follow up with the written answers. If you'd like to receive the slides from today's presentation, please let us know during the survey that will appear at the end of today's session. So don't hang up until the survey appears and you've answered the questions. We're also happy to send you a certificate of attendance after today's webinar. You'll see a question on the survey about getting a certificate. Answer yes, and we'll send one to you. A recording of this webinar in full will be available on the Accelix.com website within a day or two. And that's it for housekeeping. Now for the main event. Today, we are very pleased to have with us Don Donofrio, a veteran motor maintenance and testing expert. He'll be presenting on electric motor testing technologies. Don is the technology lead for electric motor testing and power quality analysis at the Snell Group, a Bar, Vermont-based international consulting firm. As an instructor and practitioner with Snell since 2001, Don has been integral in developing a series of innovative vendor-neutral motor testing training courses. During his 46 years overall of operating, maintaining, and testing electric motors and motor circuits, he's worked on motors rated in ounce-inches of torque on up to NASA wind tunnel synchronous motors with 80,000 horsepower. Don's diverse electrical, electromechanical, electronic, and sound motor knowledge is founded in his 20 years with the U.S. Navy Nuclear Submarine Service. He instructs both energized and de-energized motor and motor circuit analysis courses, as well as level 1 infrared thermography. Welcome, Don. Thank you so much for being with us today.
Thank you very much, Leah. It's a pleasure to be here.
Let's have a look at your introductory slide, and then I believe we have a poll question to get us started. Are you able to forward the slides?
We got a minor little lock up here like we had earlier, but it should clear here in a second.
That's all right.
There we go.
There we go. All right. Why don't you let us know if there's anything you want to share here before we move on to the poll?
No, we're pretty good here. You covered my background pretty good.
Okay. All right. So audience, you are mostly familiar with this. Don, if you'll forward to the poll slide.
All right, let me do a quick introduction to Snell here. Snell Group is a company that was established in 1986, and we currently have offices in Vermont and Missouri. We're primarily a knowledge-based company, and we offer 2 condition-based technologies with 3 service platforms. The 2 technologies are infrared thermography and electric motor testing, and we offer training, and that can be either in-house or on-site, consulting, and turnkey inspection services for both. And here we are with the poll question, Leah.
And there we are. All right. So, audience, you are very familiar with this practice. I'm going to launch the poll now. Your question is, how much experience does your company have conducting motor tests? And you only get to answer once. Our purpose here primarily is to let Don know what kind of folks are in the audience today. And then we will share the answers with everyone once we have about 75% or so of the audience sharing their level of experience. So do you think your company has advanced experience in conducting motor test, intermediate, beginner, never tried it, or not sure? And we are already just about there. I'm going to give it about 10 more seconds. So just click the best answer for you. And then we're going to share our results. Nice job, audience. Okay. And Don, here are the answers. We have 10% in the advanced category, 43% in the intermediate group, 33% in the beginner, 12% never tried it, and 1% are not sure. You have a lot of active people in the audience today.
Yeah, I'm amazed because there's still a lot of industrial facilities out there that don't even use a megohm meter.
What?
So I kid you not. It's hard to believe in a lot of cases it's the 21st century. So I'm really impressed with the poll results there.
Well done, audience. I'm going to turn it over to Don because you've got a lot to share with us today. So go get him.
All right, so this presentation, it's meant to kind of give you an overview of all the capabilities of electric motor testing. This is something that we have two 32-hour courses to cover, and I'm trying to cover an overall aspect of it in less than 50 minutes. But the important thing is, why do we test electric motors? It might be quite a shock to you, but in the United States alone, 25% or close to it of all power consumed is consumed by electric motors. Depending on the industrial process, anywhere from 60 to 90% of the power in that facility could be consumed by electric motors. Another interesting fact, motors cost about 5 to 12 times their initial purchase cost in energy consumption in the first year. So if you take average utility costs, a 25 horsepower motor running all year long is going to cost you about $15,000 to operate. A 100 horsepower motor would run about $56,000. So that's a considerable expense. And you think of the number of motors you have in your facilities, that could be a considerable utility cost. Motor energy consumption should be a concern for everyone. Unfortunately, at a lot of facilities, motors are like the roof. You don't really think about it until the roof starts leaking or the motor burns up. All the mechanisms that lead to motor failure cause an increase in the operating temperature of that motor. That increase in temperature causes the insulation to become dry and embrittled. And then under the operating stresses, primarily starting, it cracks, and that allows dirt moisture to get in there and eventually the windings short out to ground or between phases. Motor testing identifies those failure mechanisms that cause that. Now, what really got the ball rolling on motor testing and why I'm here is in 1986, EPRI, which is the Electric Power Research Institute, it's a conglomeration of utility companies, and they get together and they fund studies that mutually help out with the power generation industry. In 1986, they funded General Electric to conduct a study on the causes of motor failures. Now, these motors were medium high voltage utility corporation type motors. And of no surprise, the number one failure was bearings, and that was 41%. Of a big surprise was the fact that 37% were stator, 10% rotor. So you take those two components, that's 47% that are electrical faults. 12%, that was a bunch of different miscellaneous things such as misapplication, that type of stuff. But to go a little bit further, of that 41% of the bearing failures, there was no determination how many of those bearing failures were electrically induced. So we could have upwards of 50% of the problems that were electrically induced. And at that time, there was no really specialized available electrical motor test instruments. And because of that, Baker Instruments started making more general purpose motor test instruments. PDMA came out of that. All Test started making more and more instruments for testing motors. So, and that's, I got in when I got out of the Navy in 1994, I started work for PDMA Corporation. Now, some more interesting facts. Each year, more motors are repaired than are sold new. It works out to be about a 2.5 to 1 ratio. It's estimated that motors are repaired approximately every 5 to 7 years, and they're frequently operated for 20 to 30 years. The Department of Energy says that if we spend more time paying attention to our motor management, that we can reduce our energy costs by as much as 18%. I don't know about you, but I'd like to save 18% on my electric bill every month. According to EPRI, which is the Electric Power Research Institute, the efficiencies of mechanical equipment in general can be increased typically by 10 to 15% by proper maintenance. So that's why we want to test our motors. And when we get into the testing of motors, there's two basic classifications. We have De-Energized testing and Energized testing. These are two completely different technologies that provide a lot of similar results. De-Energized testing, of course, the motor is going to be shut down or de-energized, and it's going to provide us the safest means of testing. Unfortunately, because the motor being needed to be shut down is going to provide us the least opportunity for testing. Everybody's in high productivity mode, so there's very few opportunities to test motors when they're down. The biggest benefit of de-energized testing is it enables us the ability to assess the insulation. Now, the energized testing, this is going to be the most common means because we can check things when they're running, and most of the stuff is running most of the time. It's going to give us a power quality snapshot. It's going to provide us with current and electrical signature capability. We also have one instrument manufacturer has a torque analysis capability. And if you have partial discharge equipment, you can test insulation in a very limited capacity, usually on medium and high voltage motors when it's running. But it's not really practical for all of your motors. Now, first thing we're going to talk about is de-energized motor testing, and it's you can see several images of the most common testers over there to the right. But it's excellent for testing circuit connection faults, cable faults, winding issues, rotor anomalies, and also we can look at our protective circuitry such as surge and also power factor correction circuitry. It's an excellent tool for motor acceptance. You start testing all of your motors before they go into your warehouse inventory, whether it's a new motor from the original equipment manufacturer or if it's a repaired motor from a motor repair facility. You test it, and if it doesn't meet your acceptance criteria, it doesn't go into storage. It's great for troubleshooting. You have a motor that's sporadically tripping or drawing higher current than normal under the same load. You can go out and take a look at it. Equipment commissioning. Anytime you install a new motor or new piece of equipment, you should be out there checking it to make sure that there's no problems to start with. And then, of course, the most powerful application is condition monitoring, where you go through on a set periodicity and you check this stuff and you look for stable trends, or you look for changes and then try and figure out what caused that to happen, whether it's normal or whether it's a developing problem. Now here you have a sample motor circuit. To the left, you see your main bus and power distribution, and then that feeds the motor control center, and then we break it down into individual buckets and go out and supply our individual motor loads. Well, most of the testing is going to be facilitated at the motor control center. Sometimes you can go to a local disconnect and get in there, but for the most part, our de-energized testing is best to get as much of the circuit as possible, because it all feeds the motor, and we can have a problem anywhere and it could cause the motor to fail. But normally we're going to hook up on the load side of the contactor, usually downstream of the overloads. It's difficult to connect up on the overload, so call that the T leads. And then we read out through the cabling, through any connection boxes, disconnects, through the motor and back to the MCC, motor circuit evaluation or analysis. Now, some of the capabilities that we have is we can measure resistance, inductance, impedance. We can determine phase angles. We can use these values and do fault localization, whether it's a rotor, stator, circuit problem. Another test that's unique to all tests is current frequency response. We can do a rotor influence check. We can measure capacitance and resistance to ground. Surge and high pot testing, step voltage testing, and then a variation of resistance to ground testing is called time resistance testing, where we actually operate a megohm meter for a specified period of time. Now, resistance is quite simply opposition to circuit current. And the problems that are caused by high resistance cause the connection to heat up. And if the heat goes up, the resistance goes up, the resistance goes up, the heat goes up, and eventually it will become thermally unstable. And if you don't find the problem, it's going to find you. It'll usually open up and then you'll have a single phase problem and circuit protection doesn't work and you start burning stuff up. But the things that cause high resistance, loose or over tightened, improperly torqued connection. How many of you out there use torque wrenches and torque drivers? It's sad to say, but it's probably about 10% of the facilities use torque checks. Poor crimps, frayed conductor strands, improper wire and lug sizes, corrosion, or multiple conductors under one lug are just a few examples of things that can cause high resistance connections. Now here's a case study, and these connection anomalies, they can occur very rapidly or they can take a while. The one on the right, you can see there the two columns, one test date was 7/5/2001, and then on April 2003, you can see it's at 6.35% resistance unbalance. So you have it circled and it's in red. And the way you can tell where your connection problem is relative to where you're testing is you read 1 to 2, and you can see ohmic value 1 to 2 is 8.9 ohms, 1 to 3 and 2 to 3 are 9.8 ohms. So the higher resistances are measured in conjunction with phase 3. So phase 3 would have the problem relative to where you're testing. And again, these can happen very rapidly. I've had serious problems develop in less than 3 months, and then I've had them take a year or more to develop. But if you use infrared and motor testing hand in hand, they work very well in finding these problems. Now, inductance is another critical measurement. It's opposition to changes in circuit current and everything inside the motor, the windings, the air gap, the rotor position, all of those things are going to affect inductance. So it's a critical measurement parameter that needs to be monitored. If you have power factor correction capacitors, if you have a problem with them, that'll have a drastic effect on your measured inductance. Here's a case study where we were trending inductance, and you can see it's over a period of several years, and it's kind of up and down, but it was staying pretty consistent from about 4 up to about close to 6, and then all of a sudden it just skyrocketed and started climbing. We did some correlative testing and determined that there was broken rotor bars. So you can see how that can help you. Now, impedance and phase angle, these are some valuable information because you should see symmetry when you're measuring all 3 phases. If you start seeing a disparity in the impedance angle or the resistance or whatever, you know whether you've got a connection problem or a winding problem or a rotor problem, and we can start narrowing it down. And phase angle is very important because that angle also represents the voltage and current phase angle when the motor's in operation. And again, it should be the same for all 3 phases. Current frequency response, this is a test that's used by all tests, and basically what they do is they'll take a test measurement at a given test frequency, and then they measure the amount of current coming back through the circuit under test. Then they double the test frequency. If you double the test frequency, you double the reactance, and the reactance is measured in ohms. If you double the ohmic value of something, you're going to cut the current in half. So by doubling the test frequency, we should see about 50% of the current that we had on the first test. So what we're looking for is balanced current in all 3 phases. And if we don't see that, then we know we've got some kind of a problem. And it's very sensitive to winding issues. So it's a great test. But we're looking for balanced response in all 3 phases. Now here you can see capacitor box, and this is be an individual load power factor correction cap. And you can see in the schematic there in the middle, it kind of taps off on the load side of the contactor in parallel with the motor windings. And if you have one of these capacitors open, it's going to throw your impedance vector way off. And that's why it's important to know if you have these installed, because otherwise you might think you have a serious motor problem when in fact it's just capacitors. But the capacitance is going to have an 180 out effect, or complete inverse and opposite effect on the inductive reactance. So by adding them in there, we're going to lower that impedance angle, the red angle on that vector there. We're going to get it closer to the resistance angle, or horizontal. If it was laying perfectly on there, our power factor would be 1, which is the cosine of 0 angle. Now, here's how we can do fault localization using resistance, inductance, impedance. If I have low unbalance in all of them, then everything's normal. If I have a low resistance imbalance and I have moderate inductance or impedance imbalance, then I start looking for the rotor. If I have moderate resistance imbalance and inductance and impedance, then I might have a stator fault. I've got windings shorted or something. If I have a low resistance unbalance and very high inductance and impedance unbalance, then I start looking for defective power factor correction caps. And if I don't have a rotor installed and I have balanced resistance and unbalanced inductance or impedance, then I look for improper jumpers or a reverse coil or something in the motor winding. So this comes in handy in motor shops as well, making sure they're doing a good quality assurance on their rewinds. Then we have the infamous rotor influence check. This is going to be a measurement of inductance over an angular rotation of the rotor. Normally want to start with key way up, and then you're going to do 18 successive tests over an arc of a pole group. So if I have a 4-pole motor, I would do 90 degrees. I could do a full 360, but this test takes a considerable amount of time. The 18 tests is so that you have really good resolution on the graph that this plots out. And the best results are going to be obtained if you run the motor at load and then shut the motor down and then do the test. Now, it's going to give you a graphic representation of the inductance relationship between the rotor and the stator. And if you look at my top left, you can see a symmetrical sinusoid for all 3 phases. That's great. That's what you're looking for. If you look at the top right, you can see where there's distortions, and this is a full 360. And there's distortions are moving as the rotor's turning. And that means that the problem is in the rotor. So you could have a porosity in a cast rotor or broken rotor bars or something like that. The bottom left is a high quality rotor, a medium high voltage rotor with copper bars instead of cast. And you can see there's barely any change at all in that line. But if you have a problem developing those rotors, you will start seeing separation on that brick plot. The bottom right is a concentric wound motor. This is the way most of your new low voltage motors are going to come from the original equipment manufacturer. The windings are pancaked in and they're not all equidistant from the center bore of the stator, and they're going to give you this slight disparity in the inductance. Here's some more. The top left, notice that the 2 phases on the bottom have dropped. And that's, if you look over at the key on the right, 1 to 3 and 1 to 2 have dropped. That means the problem's in phase 1. That would be a turn or coil fault in phase 1. And whenever we measure it in conjunction with another phase, we get lower inductance. Same thing on the top right. It's a turn or coil fault in 1 phase. The bottom left, notice it starts off high, it goes down low, and then climbs back up again. That means that the rotor is not in magnetic center. It's moving around in that center bore. It's eccentric. And then the bottom right, we only have 1 phase that dropped. You see the green sinusoid drop, the blue and the red is up. That's a phase-to-phase short. It's in phase 2 to 3. So these Rick patterns can be pretty useful if you can't run the motor. But I can find out all this information within about a minute and a half running the motor. But if you can't, this is an excellent tool. Capacitance is another good parameter to monitor, capacitance to ground. So when we measure capacitance to ground, we're essentially reading from the stator slots to the windings. And what happens if I increase the plate size of a capacitor? I increase the capacitance. So essentially, if we add more and more contamination onto the motor windings, we're increasing the plate size of one of the capacitive plates because we're measuring to ground. And so as capacitance starts climbing on a motor, that means that the windings are getting dirty. I start putting more and more contamination buildup on the windings, what happens to the motor under normal operation? It starts running hotter. So using capacitance to ground, it's an early warning system for the insulation health. Now, insulation testing is probably the most important test we can do because all of the conditions that cause motor failures cause the insulation to thermally degrade. We have resistance to ground testing, which is basically a megohm meter test, high pot or high potential testing, and that can be both AC or DC instruments, surge testing, and then time resistance testing with a megohm meter, which would be the Polarization Index dielectric absorption test. Surge testing is simply a variable output transformer charging a large capacitor. Then we discharge it between the windings, 1 to 2, 1 to 3, 2 to 3, and you can see that decaying waveform there on the right. Some people call it an impulse. Some people also call surge testing impulse testing. But that waveform of that capacitor discharging through the windings is what we're looking for. And it should be the same in all three phases. If it isn't, that could indicate different types of problems. Now, up until the mid-90s, this was a pass-fail test. You increase the voltage in increments up to the maximum test voltage for the operating voltage of the motor under test. And if it made it up there and didn't fail, good, the motor's good. If it didn't make it, you'd have to rewind the motor. So it was pass-fail. In the mid-90s, Baker Instruments developed a sensitive triggering circuit. So whenever the current started to ramp up, it would shut down the power supply and it would indicate that you had a weak insulation. So that provided us a great reliability centered maintenance platform for surge testing. Here, just some examples of the different types of surge test waveforms and the different types of faults that they represent. I'm not going to spend a lot of time on there, but most of the newer surge testers, this is all computer automated. It tells you what the problems are if you have the right nameplate data entered into your database. Another innovative thing that Baker Instruments came up with, Baker, by the way, is now owned by Megger Corporation, but they came up with what they called a pulse-to-pulse error area ratio. Surge testing requires that the rotor has to be installed or removed, and with the pulse-to-pulse EAR, we could leave the rotor installed. And it's not looking for the symmetry as much as the successive waveforms. So if I charge a capacitor up at say 200 volts, and then I jump it up to 250, and I jump it up to 300 and 350, the magnitude of that impulse wave is going to climb, and it's going to climb at the same amount with each equal increase in voltage. So what the pulse-to-pulse EAR does is it measures the difference between the successive pulses, and then it measures the difference between the baseline and the peak of each successive pulse. And it should be the same if the incremental steps of voltage are the same. If I start having weak insulation, that's going to change, and it's going to alert me that there's a possible breakdown starting to occur. So it's really great because we can do this with a motor installed with the rotor and use it for reliability. Here's an indication of weak turn to turn. You can see the top red waveform. You can see the successive pulses. It's stepping in 500 volt increments from 500 to 1,000 to 1,500. Then the one below it is the other phase. It's in blue. And then the yellow phase, you can see they made it up to 1,000, but when they went to 1,500 volts, you can see where the white line was breaking down. High potential testing is just that. This is testing the insulation to the max. And again, this is a pass-fail. Some of the other newer instruments have sensitive triggering on it, but you are going to test this motor to the maximum capability for the insulation to ground. For example, if you look at the table on the right, a 480 volt motor, we're going to test at 3.4 times the line voltage plus 1,700 volts. So 480 volts, we're testing at 332 volts. For an in-service motor, we'd take 65% of that. We'd test it at 2,165. So major stress test on the motor. And this is used in, like I said, both AC or DC instruments. Usually AC is used on your high voltage distribution system and cablings, and then DC would be on motors and motor circuits. Time resistant testing. This is a megohm meter, and we're going to test for a period of time. So we have polarization index. This is a 10-minute megohm meter test. And if you graph the results, you're going to get unique patterns indicative of different insulation conditions. We basically break these patterns down into 5 different ones: normal, and then 4 anomalous patterns. And here are your 5 basic patterns. Top left is normal. You see it starts off low and climbs, gives the indication of climbing over time. Then you have a low ground. It comes up at a very, very low level and then flat lines out. And then you have tracking. And this is usually caused by dirt or moisture on exposed uninsulated terminations within the motor circuit. It'll reach a certain potential to ground, and then it'll discharge and charge and discharge, charge and discharge. And that's why you're seeing that erratic sawtooth looking pattern there. Usually if you go in and clean all those exposed terminations, you'll go back to a fairly normal pattern. Excuse me. And then bottom left, embrittlement. That's just that, though. Insulation's old and dried out, and it takes a long time for the insulation to polarize. So you see that really steep slope. And then severe breakdown. This is the worst one you'll see. This is like if you were pressurizing a fire hose, as an analogy. Once you reached a certain pressure in the jacket of the hose, it ripped and all the water started pouring out. Well, that's what that means for your insulation. You've got a rip in the hose. Here's a case study. This was a DC generator, the one on the left, and at a steel mill. And I told them, hey, you guys need to take a look at this right away. They determined they were just going to go ahead and start up, and a day later it failed. The one on the right, if you can read that, it actually goes up above 2,000 megohms, which nobody's going to sneeze at that being a bad value. But if you look at it over time, it drops down to below 1,600. Excuse me. So that's indication of severe insulation breakdown. It's less at the end than it was at the beginning. And if you look at the first image there in the middle, what was happening was that splice was rubbing against the motor connection box cover, and just the inherent vibration of the motor normal operation, it abraded that insulation and it started arcing. And in the right-hand image, you can see where it was arcing to the cover. Now here, this was just a low ground. Excuse me. This was a mill in Kansas, and they just added this whole new facility, and it was a 4160 250 horsepower motor. Their minimum spec was 100 meg at the starter out to the motor, and you can see right below that it's at about 42 meg, I think is what it got up to. So it failed that test. So what we did is we had them disconnect everything at the motor, and we went through the next day and checked the 3 dead-ended cables, and all 3 of them are reading about the same, about 14, 15 meg. And that is rarely rare that you will see that on all 3 cables. They'll all be different. So looking for something in common with those 3 cables that are open-ended at both ends, open contactor and open leads at the motor. We went to the starter, and if you look at the top image in that circle, you can see that bakelite insulator where the motor leads are connected going out into the cable run. We lifted the phase 3 lead off of there and then read it, and it immediately went to 21,200 meg in 5 seconds. And it ended up close to 95,000 meg with a 2.43 PI, with 2 being good, after the 10-minute test. So it was that insulator that was bad, and that could have caused a failure later on down the road. So this is a case of commissioning. We found a major problem. Here's another one on the left. This is 2 different problems. The one on the left was a boiler ID fan. The main fan had bad bearings. They were putting their spare in. They asked me to test the motor, and I did, and I test the cabling. And if you notice, it's a real steep slope. That means possible embrittlement. Well, using common sense, the cables run next to a boiler. The boiler's hot, dries things out. I recommended they replace the cabling, and once they saw the expense of the job, they decided they weren't going to do it. 6 months later, that cabling had to be replaced. It failed. The images on the right were from the same plant. It was a medium density fiberboard plant, and they installed a biofilter to get rid of all the sawdust that was in the ambient air. And all the motors in the biofilter were about the same size, so all the same cabling. And every one I tested was reading about 10, 12 meg. So we disconnected some of the motors, tested the motors, and motors read fine. So we determined it was bad cabling. They ended up pulling all the cabling out. You can see it staged there on pallets, being sent back to the manufacturer for replacement. All right, step voltage is another type of time resistance test. And it's, instead of looking at current, we're looking at voltage and current. And you step the voltage in equal increments, and you should see an increase in current with each step in voltage. So in this example here, we're starting off at 250, then going to 500, 750, and 1,000. And the graph on the right is the current, and you can see we went up to about 1.5 amps with 250 volts, and we went up to 3 amps with 500, and so on. It was symmetrical with each step in voltage. We saw a symmetrical step in current. That's what you normally see. If there was some breakdown, you would see a jump in the current, and it wouldn't be symmetrical, and you know at what voltage it's starting to break down. And it's a non-destructive test, so we can see something and repair it rather than destroy it. I do this for baselines or whenever I have a unstable polarization index. All right, here we are at poll question 2. I'm going to turn it over real quick to Leah, and then we'll get back to energized testing.
Thank you, Don. All right, audience, warm your fingers up. If you cannot see the radio buttons, by the way, you may need to reduce the size of your screen. And thank you, everyone. You're already going. Here's our question. How applicable is motor testing to your plant or facility? Is it highly applicable, somewhat applicable, not very applicable, or not sure? And Don, thank you very much. That was a masterclass in de-energized testing. I really appreciate that you have synthesized your material. Audience, you've got 66% of the audience voting now. Let's get another 10% in, and then we're going to share the results with Don. Excellent, well done. All right, I'm going to share the results now. We have 51% feel it is highly applicable, 37% say somewhat applicable, 7% not very, and 5% are not sure. I'm going to guess that the second half of the presentation will illuminate further.
I hope so.
All right, Don, I'm going to share this back to you, and off you go.
All right, thank you. All right, now the second part is energized electric motor testing. Like I said, this is a completely different technology, but it will identify a lot of the same failure mechanisms, just look at it different. And what it does is it entails connection of voltage leads, 3 leads per phase and a ground, amp probes, and we can connect directly on low voltage, less than 1,000 volts. And then for medium high voltage, we're going to connect on the secondary circuits, the CTs and PTs. And it provides a means of assessing power quality. And then we can also look at current and electrical signature and perform analysis on that. It also provides a means of identifying many of the failure mechanisms that lead ultimately to motor failure. And most of the OEM instruments do not assess insulation integrity, as I mentioned before. And a lot of people are very leery of energized testing because we're in the vicinity of energized gear, but it can be incident-free if safe practices and procedures are followed. Now, energized motor testing provides an expedient testing method for identifying for power quality problems, motor and motor circuit electrical issues, drive and drivetrain issues, and a lot of the failure mechanisms that lead to insulation breakdown. It's an excellent tool for troubleshooting, equipment conditioning, condition monitoring, and power quality, fault isolation, and localization. And then you see 3 instruments there. The PDMA is at the bottom. The top left is the Baker, which is now Mega Explorer 1 and 2 series, and the AllTest Pro online. Now, power quality, there's a lot of things that we can look at. I'm just going to briefly go over the list. You have high frequency events, unidirectional oscillatory impulse, voltage fluctuation. When you see the lights flicker in your plant, that's voltage fluctuation. Voltage sag swells, notching, zero crossing, transient over and under voltages, unbalanced voltage and current, reactive current unbalances, power factor issues, harmonics. We'll talk a little about them a little bit. You have even, odd, zero, mechanical, and sequence currents. And frequency deviation, which you just don't see anywhere, but it's a potential problem. But we'd be able to see it with energized testing. And then ground anomalies. All right, so here's some power quality items here. And again, these things happen so fast. We're talking a small fraction of a second. You're seeing a pulse in a portion of a half cycle of something that's 60 cycles per second. So if you're not hooked up when it happens, you're not going to see it. So they don't have event logging capability. I think the alt test does, but it's for a short duration. But if you can see the top one there, there's a positive pulse. It's happening on the positive direction on a positive half cycle. And then you see over on the side that's slight negative. That would be a negative event. If it covers both the positive and the negative in the same half cycle, it's called oscillatory. And then a very major problem, especially if you have timing circuits that are based on when your sine wave passes from negative to positive or positive to negative at that zero crossing. A lot of circuits are timed at that point. And if you have notching occur right at that crossing, it'll throw the timing off. Then you have voltage fluctuation, flicker. You can see the sine wave there at the bottom left. It's not consistently at the peaks throughout the waveform. And then over on the right, we could have normal, we could have voltage sag swells or interruption. Now harmonics, these are multiples of the fundamental frequency. They're basically an electrical echo. So I have 60 hertz, the multiple of that would be 120, 180, and so on and so on. And 50 hertz in Europe, or whatever the frequency is coming off of a frequency drive, a harmonic of that base frequency. There's differing schools of thought. There's a lot of people who don't think they're harmful, they think they are harmful, but it's prudent to believe that they are and monitor accordingly. And there is absolutely no doubt whatsoever that they produce heat. And they produce heat at the square of the number of the harmonics. So if I had equal values of the first harmonic and the second harmonic, I would have a lot more heat generated on the second harmonic. So here's the harmonic sequence. And you can see the 1, 2, 3, 4, 5, 6, 7, 8, and so on. The first harmonic for 60 hertz would be 60, and it would be a positive harmonic. In other words, the harmonics are going to be aiding the positive direction of the waveform. 120 hertz is a negative. It's going to be opposing the development of the positive and the negative portions of the 60 hertz waveform. Then you have 180, which is a zero harmonic. It has an equal number of positive and negative pulses, but this one is an odd multiple of the third harmonic. So it's got its own unique identifier, and it's called a triplen. The unique thing about triplen harmonics is they have a tendency to feed back upstream, and they will get into our transformers, and they can cause a lot of overheating and cause some real deleterious effects on our transformers and motors. Then you go to 240 hertz, it's positive, 300 negative, and 360 zero. Now, that's an even multiple of the third harmonic. It's not a triplen. If you go up to the 9th harmonic, it's a zero triplen, the 15th, the 21st, and so on. Those are triplen harmonics. The most important thing in power quality is voltage analysis. Okay, and we're going to check for balance phase to phase, phase to neutral, look for harmonic distortion. Voltage balance is extremely critical. And if we have unbalanced voltage, we can have some really serious effects caused by that, because it's also going to cause unbalanced current. Here you can see some displays from the Baker instrument, alt test, and PDMA. Now, like I said, voltage should be viewed first, and you want to make sure you get your voltage straightened out before you do anything else, because it's going to skew all your other values. You see phase to phase, phase to neutral voltage representation in a time domain up there at the top, and then down below you see phasor diagrams for voltage to neutral and then voltage phase to phase. As little as a 3 to 5% phase to phase voltage imbalance will cut a motor's life expectancy in half, because it's going to cause that motor to run much hotter. I mentioned that we could find ground faults with an energized. If you have a ground on a common bus on an ungrounded system, and you look at your voltage to neutral, the phase that's common to the ground, the voltage will start dropping off as the ground gets worse and worse. So if I had a zero ground on a 480 volt system, normally I'd have 277 volts to neutral. It would be at zero, and the other two phases unaffected would be at 277. And if you look at the time domain captured down on the bottom of current, notice you have the real high red and blue phases, and the black is right on the center line or baseline. Then all of a sudden you start seeing a normal waveform. Well, they shut a piece of equipment down that was grounded, which isolated it from the bus. We went back to normal. And you can see the same thing on the one to the right. So with the isolated ground from the bus, everything went back to normal. Current, we want to have balanced current, proper phasing, in other words, 120 degrees between the phases, and we don't want any distortion like you see in that waveform up at the top, the time domain. Look at how distorted the voltage and current is. Now, with the current and impedance values that you get from your energized data, it's just like we were looking at for inductance and resistance. If the current unbalance and impedance imbalance is low, like 3 to 5%, everything's normal. If I have a moderate current unbalance and comparable impedance unbalance, I have a connection problem developing. I have a moderate current unbalance and a 2 times or greater the current unbalance for impedance, then I have a Stator fault. I could have some coils or turns shorted. And if I have a moderate current unbalance and a real high impedance unbalance, 50 to 80% higher, then I'd start looking for defective power factor capacitors. Now, electrical signature analysis. This is another great capability of energized testing. This goes above and beyond power quality analysis because this is going to break down our current. And we can look at current, we can look at voltage, we can use various spectral formats, and we can analyze for electrical and mechanical anomalies, and we also can do some fault localization. So the first thing we can do is we monitor motor starts. So when you hit a start button on a motor, that current jumps up significantly. That's inrush. Be anywhere from 2 to 10 times the full load amperage on a motor nameplate. And we can monitor that inrush. We can, how long does it take the transition to run? We can look at the confirmed rotor bars. If you look down on the bottom there, you can see an overlay. The baseline was normal, and then the black line was broken rotor bars. It actually had less current because there's higher impedance on the rotor, and you can also see the distortion caused by the magnetic coupling anomaly between the rotor and the stator. We can look at load evaluation. We can check timing circuits on time delay relays and stuff like that. We can check the start circuit, and we can trend all of this. And then we can actually figure out what we have just by what our indications are. If the peak is normal and the transition to runtime is normal, everything's good. If it's low in one channel and longer to transition to run, I got a high resistance connection. If it's high in all channels and longer to transition, then I've got a mechanical load problem. It's requiring more torque and more time to get the motor up to speed. Lower in one or more channels and longer transition to runtime, then I've got a rotor fault, broken rotor bars or something. So there's a lot of powerful stuff here that we can use to narrow things down. Here's some examples of inrush. It's just single channel. There's a 75 horsepower cross the line. Look at that, it's up to about 350 amps. Here's a 400 horsepower motor on a soft start. Notice it only goes up to about 900 amps. That could go up to 3,000 or 4,000 amps if it was across the line. And if you look at about right below 10 seconds, you can see that peak where the soft start times out and it transitions over to across the line. Here's a couple more. Here's a 4,000 horsepower on a start reactor, which is basically a transformer that's in the circuit for the startup. And that transformer winding is going to reduce the voltage. It's going to have a voltage drop and reduce the current going to the motor. And then on the right, you have a variable frequency drive on start. Here's a 6-channel capture of all 3 phase currents and voltage on a VFD, and everything was good. And then here's that same motor 3 months later. I tested this thing in like December, and then they called me up and it failed in January, and it burnt the motor up. And they put the motor back in. I said, do not run that motor until I get a chance to test it. This is what it looked like when I tested it. The drive went bad, and you can see the partial waveform for the red phase and the blue phase. The only phase that's normal is the black one, which is phase 1. So they had to repair the drive, and then everything went back to normal. All right, here's a couple other case studies. This is a 50 horsepower 2-speed fan. It starts in normal and slow, and then shifts to fast. And then the bottom one, they had it wired backwards. It started fast and went to slow. Electrical signature analysis and motor current signature analysis. This is where we take a time domain, which is a sine wave, and convert it to a frequency domain. Let's say I have a 60 hertz sine wave, and I have a bunch of other frequencies that are riding on that fundamental waveform, and they just make a small percentage of the total waveform, but they're going to cause distortion in that wave. What an FFT or fast Fourier transform does is it samples that sine wave multiple times, and it determines all the rider frequencies and their amplitudes, and then it segregates them out. So looking at the green arrow to the left, I'm looking at the time domain. Looking at the burgundy arrow to the right, I'm seeing the frequencies, the component frequencies that make up that total waveform. Every one of those frequencies is caused by something. Our job is to figure out what it is and whether it's normal or whether it's problematic. All right, here you have an overlay of voltage and current. And by using this, whichever is dominant will tell you where it's coming from. So if voltage is dominant, that means that that frequency is coming from upstream of where you're testing. If the current is dominant, it's coming from downstream from where you're testing. If it's in current only, then it's a mechanical problem and it's downstream from where you're testing. So this will give you some, and eventually when you find the one that's causing the voltage problem, you're going to see it affecting the current as a dominant. So it helps you narrow things down. All right, here's rotor bars, okay? When you have a broken rotor bar, that rotor's turning in the center bore of the stator, and that region of the rotor where the bar is broken or open, eventually the adjacent bars will open and you'll have a dead spot there. As that spot passes the field poles, there's no magnetic field interaction, then there's a jump. That jump causes side bands on line frequency. So if you see that little stick drawing down at the bottom, you see the 2 side bands on either side of 60 hertz. Those are going to be indicative of the RPM and the severity of the rotor condition. And you can see the table there, 54 to 60 dB. This is down from 0. Everything's good. So as the numbers get smaller, the severity of the rotor problem gets greater. So if I'm less than 36 dB, it's time to secure that motor and replace or repair the rotor. Here's an example of broken rotor bars. You can see the side bands with the X there on the right, equidistant from the 60 hertz, and then you can also see some harmonics on either side of those. Eccentricity. Eccentricity simply means the rotor is not operating in magnetic center. We can very easily see that with current signature. And eccentricity means that the rotor is either radially, axially, or a combination of the two out of magnetic center. And the types, we have static and dynamic eccentricity. And the static, it's moving around in the center bore of the stator. And here you can see the indications. If it's static, I just get 4 peaks, which are based on the number of rotor bars times the RPM of the rotor, and divide that by 60 to figure it out in frequency, in hertz. If I have dynamic eccentricity, I see the pole pass frequency side bands on either side. It just means the rotor is moving around. I can also locate stator mechanical faults, but instead of rotor bars times the RPM, I take the stator slots times the RPM, divide it by 60, and I'm looking for those 4 peaks. And that tells me I have core movement or loose coils in the rotor. And then over to the right, mechanical imbalance or misalignment. I'll still have all the 4 peaks for eccentricity, but from that first peak to the right, I'll have a 240 hertz peak and then a 120 hertz peak. Here's an example of one that I found in a field on a ground storage pump at a CPW site. They had just replaced the pump impeller and they didn't get everything aligned right. So look at the top spectrum there. It says a DMOD spectrum. You can see the RPM peaks at 20 hertz and the 2 times that at 40. You can barely see them. Look at what happened when it was misaligned. Down at the bottom, you can see how elevated those peaks are for the run speed and 2 times the run speed. So this stuff will jump right out at you when you have a problem and you know what to look for. Here's an example of rotor axial movement. The rotor's moving back and forth in an axial plane, and it causes a split peak at 300 hertz. Belt frequencies. If you have misaligned, belts are too tight, eccentric shifts, etc., it's going to give you 4 peaks that are going to be below the RPM of either the drive or the driven shift. So this is a nice capability to have. They'll jump right out at you as well. Mechanical faults, we can find blade pass frequencies. So impeller blades on pumps or fan blades, if they're out of balance or bent or missing blades or whatever, it's going to cause variations in the torque, which is also going to cause distortion in the current coupling between the rotor and the stator, and we can see it. We can also find bearing problems. Here you can see some indications of bearing problems, but when you start seeing bearing problems in current signature, fire your vibration guy, because he should have seen these about a year before you start seeing them with current signature analysis. And that is a completion of an overview of electrical motor testing for both energized and de-energized. And like I said, we cover this in 2 32-hour courses, and we also have a combined course which condenses a lot of it. But this presentation was meant to be a brief introduction to all these motor test capabilities. And if you guys are interested, I'm sure we can set up some more involved presentations on just about anything you're interested in as far as motor testing. But if you have any questions or you want more information, you can go to info@thesnellgroup.com or contact us at www.snellgroup.com, and there's some phone numbers there for you to copy down. I'll give you about 15 seconds to write anything down from that. Then I'll proceed.
Thank you, Don. This was a masterclass in 50 minutes, and I am just stunned at the level of, I guess, the comprehensiveness of what you're able to share. And we do have lots of questions, and I want to encourage people to continue entering their questions. We will get back to you after the presentation if we're not able to answer them all now. I want to continue sharing what you've got here.
All right, so on our website, there's free white papers for both infrared and motor testing, and you can sign up for a free newsletter. We're not going to share your email or anything, just give you knowledge information on infrared and motor testing. And then this is, if you're doing motor testing already, these are a valuable resource. They're for sale, very reasonable, one for de-energized and one for energized data analysis. They're 3 foot by 4 foot laminated wall charts. And that is it for my portion of this presentation. And I thank you for allowing me to share this information with you.
Fantastic. So we have questions that range throughout the scope that you've presented today, but I'm going to start with a high-level one. And this reads, of the overall range of motor tests that you've highlighted, which would you say are the most essential and realistic for an organization that is not doing motor testing today to begin doing themselves? And if that same organization were to make an investment in tools, what would be the first few tools and measurements you would recommend?
The most important test to do is insulation. So if you're just starting out, get a really good megometer and go through and meg your motors and make sure that you're getting good resistance to ground readings on it, because that's what all the failure mechanisms cause, is a degradation of the insulation system.
Good. Okay. Any second runners up?
Well, if you're going to energize, if you're going to do it for energized and you're limited, I would check your power quality. I mean, that's essential. You got to have clean voltage and you got to have balanced voltage and current.
Okay. And then we've got a couple people asking which of these tests are applicable to VFD driven motors.
All of them, all of the energized and de-energized, we can run them, you know, so that you're just going to get the whatever the frequency output of the drive is, and you can evaluate them as well.
Okay. I'm going to give you a specific question here. Is it correct to conclude that triplet harmonics are the most potentially destructive?
Yes, they are. Like I said, they feed back upstream, they get into your transformers. And remember, transformers are designed and motors are designed to operate at 60 hertz. We start putting all these higher frequencies in there, we get a thing called magnetic hysteresis, which causes heating. And it's kind of like an induction cooktop or a bearing heater. You're cooking by hysteresis, so it can get quite hot.
Okay, last question. This is another high-level one for someone who's new to motor testing. Is de-energized or energized the more proactive way to go?
Energized because your most of your assets are going to be up and running, high production demands. But when you have the opportunity, do de-energized.
Okay, fair enough. All right, audience, keep typing in your questions for a minute or so, and we will get back to you. Right now, I want to make sure that you all see this opportunity coming up on February 17th. This is going to be an awesome session. It's a full-on most dangerous jobs with Matt Joinson of Jaffray Millwright and Payam Asadi of Proof Technic Canada. They have got hundreds of stories to share and a lot of excellent advice about getting precision alignments in all conditions. So I encourage everyone to join us. And then Don, if you'll forward to the next slide. After I close today's session, there will be a slight pause and then a survey will appear. I want to encourage everyone also to complete that survey. Doing so will get you a copy of the slides. You'll have an opportunity to request a certificate of attendance, and we'll get your feedback on today's session and what you would like to learn about in the future. So please hang on a moment and answer those survey questions. And with that, Don, I want to say a huge thank you for your time and sharing everything today. It was great having you on the show.
Oh, thank you very much. I enjoyed doing it.
And thank you, audience, for coming today. We look forward to seeing you next time. And with that, I'm going to close today's session. Thanks, Don. Bye-bye for now.
Thank you. Bye.